Hi, everyone. This is our first chemistry lecture. We are going to talk about atoms, look at the structure of an atom, look at the periodic table, and talk about why this is important to know in a biology class. So let's start with just some basic definitions. And I'm going to start with the definition of matter. Matter is anything in the universe that has mass and occupies space. So that's pretty much a lot of things you can think of. In fact, it's probably most things you can think of. Has mass and occupies space. Energy does not have mass, so energy is not matter. But matter is everything else around you. It's your hair, it's your shoes, it's the desk, it's the chair I'm sitting in, it's your car, it's everything. And all matter is made of atoms. Atoms are the smallest particle you can break matter down to that still retains all the chemical properties of that element. So atoms are the smallest units of matter that an element can be broken down to, that retain all the chemical properties of that element. What do I mean by elements? I'm going to show you the periodic table of elements in a minute, but let's just assume we're talking about the element gold. One atom of gold has all of the chemical behaviors of gold. It would have the same melting point, the same boiling point, the same density. All of the characteristics of gold would still be contained in that one atom of gold. Anything lower than that would be subatomic particles. Atoms are really important to understand in biology because biological systems are chemical. There's chemistry going on all day, every day in your body. You are a big bag of chemical reactions. And to understand the molecules that make up your body and other living systems, you have to understand something about atoms and what causes certain atoms to bond together to form these very important molecules. You also need to know something about the ions in your body and the important role those are playing. So we'll learn what ions are in this lecture. There's a lot here that's really, really important. So yes, this is not a chemistry class and it's not a physics class, but you're going to learn a little chemistry and physics today to help you understand biology at a deeper level. Let's take a second now to look at the periodic table and see what these elements are that we're referring to. This is the periodic table of elements, and I'm actually going to make it even bigger here. There we go. And this contains all of the naturally occurring and man-made elements. They are all different in that they all have a different number of the 3 subatomic particles that we're going to talk about today. And in particular, it's one of the subatomic particles called the protons that really defines what element you're looking at. It's arranged in order of what we call the atomic number. And we'll talk more about what that atomic number means in a minute. But you can see in the upper left here, number 1, 2, and then we go down here, 3, 4, 5, 6, 7, and so on. This is an older version, so there are some new man-made elements that don't appear on this periodic table, but for the purposes of this class, this periodic table is fine. You also notice that every element has what's called a chemical symbol. So you see here the letter C, which actually stands for carbon. And when we're writing out a chemical formula, or either just a molecule or to show a chemical reaction, we would never write out carbon. We would only use that chemical symbol. So those chemical symbols for the most commonly occurring elements in living systems you should probably become familiar with, in particular carbon. Carbon is very, very important to your understanding of biology. It's the basis for all organic chemistry, which is the chemistry of living organisms. So also looking, you see there's a number down at the bottom, and we're going to talk about what that means. That's the atomic weight, also known as the atomic mass. And I'm going to show you in a minute on page that I'm writing on what that all means. So you also notice that everything is arranged in columns and in rows. We're going to talk today about 8 of these columns. This first one, second one, and then we're going to skip the metals, go all the way over here to boron. So this is going to be the third column, 4, 5, 6, 7, 8. These are primarily the 8 columns of elements that we're going to deal with in this class. And in fact, we're not even going to deal with all 8 of these columns. We're only going to get to a certain point here that I'll show you today. It's important to be able to know how to use this periodic table. You do not need to memorize it. You just need to know what these numbers mean. And I'm going to show you that now. So I'll start with carbon as our example, since that's the example that was shown on the periodic table of elements. So remember, C was what we called the chemical symbol for carbon. You also might have noticed that some of the elements actually have a 2-letter abbreviation for their chemical symbol. And then there was a number 6 here and a number 12 down here. And for every element on that periodic table, there are those 2 numbers. This is known as the atomic number. And this is known as the atomic mass or atomic weight. What those numbers really represent says something about some very important particles that make up the atom, and those are called subatomic particles. These are the very, very small particles that make up an atom. And in this class, we're going to talk about 3 different types of subatomic particles that all atoms have. There are more than 3, but in this class, we're just talking about 3. And those 3 are protons, neutrons, and electrons. So let's look at just a basic structure of an atom. And this basic structure applies to all atoms on the periodic table. In the center of every atom is a region called the nucleus. So just as your cells have a nucleus, every atom has a nucleus. And in this nucleus are 2 of these 3 types of subatomic particles. We have the protons, which will represent with the letter P, and we have the neutrons, which will represent with the letter N. And then orbiting outside that nucleus are the electrons. These electrons are contained in what are called electron shells. And closest to the nucleus is what we call the first electron shell. And that first electron shell can hold a maximum of 2 electrons. So there are spaces here for 2 electrons to be held in that shell or to exist in that shell. So that first electron shell holds a maximum of 2 electrons. If an atom has more than 2 electrons, which we'll show in a minute how to determine that, if an atom has more than 2 electrons, they start filling the second electron shell. And that second electron shell holds a maximum of 8 electrons. So there's room for 8 electrons to be in that second electron shell. So I'm going to show 8 spaces available. And I'm spacing them like this so that when we start looking at chemical bonds, it's going to be easier to show something very important that happens in chemical bonds if I space them out this way. But in reality, they wouldn't be spaced out that way. It's just the way we usually show it on the board or on paper so that it's going to make it easier at some point to show another story. Okay, and then finally, if the second shell gets filled, then electrons start filling the third electron shell, which I'll show here in red, and it's going to go all the way around. This third electron shell also holds a maximum of 8 electrons. So again, 8 spots available for electrons to fill. And so on and so forth. Electrons just keep filling more shells. The more electrons you get, just keeps moving out. For this class, you only need to concern yourself with the first 3. We're not going to look at any elements that have a number of electrons greater than what would fill those first 3 shells. So what do I mean by this? Well, what I mean by electrons filling these electron shells is every atom on the periodic table has a different number of protons, neutrons, and electrons. And we're going to look back at carbon for a second to figure out how to determine that. That atomic number of every element on the periodic table is equal to the number of protons in the nucleus of that atom. So all carbon atoms have 6 protons in the nucleus. We know that because carbon has atomic number of 6, and that is equal to the number of protons in the nucleus of carbon. It's also, remember, the order in which every element is arranged on that periodic table. So that means every element is arranged in order of the number of protons that it has in the nucleus. That number of protons cannot change for an element. If it's a different number of protons, it's a different element. So in the nucleus of carbon, it would have 6 protons. So I'm just going to erase this P and N here, and I'm going to draw carbon as our first example. So in the nucleus, carbon would have 6 protons. And those protons actually have a positive electrical charge. So that means in the nucleus are 6 positively charged subatomic particles. So protons, positive. Protons have a positive charge. And carbon is atomic number 6, so that means it has 6 protons in the nucleus. That atomic number also represents the number of electrons that are orbiting outside the nucleus for every atom on that periodic table. And electrons actually have a negative charge. So the atomic number of an element is equal to the number of electrons, and it's also equal to the number of protons. It's not equal to the number of electrons plus the number of protons. So carbon is atomic number 6. That means carbon has 6 protons and it has 6 electrons. That means that in these electron shells, orbiting the nucleus of carbon are 6 electrons. And here's how those 6 electrons are going to fill those electron shells. I'm going to make them yellow. The first 2 are going to fill this first electron shell because it holds a maximum of 2. But carbon has 6. So that means those other 4 are now going to start filling that second electron shell. 1, 2, 3, 4. So 6 electrons total for carbon, and they would be situated in the first electron shell, which holds a maximum of 2, and the second electron shell, which holds a maximum of 4. As the atomic number increases, the number of protons and electrons increases, and they would just start filling that second shell and then filling the third shell and so on. This is going to be hugely important when we start talking about the chemical behavior of elements, and I'm going to talk about that in a minute. We've got one subatomic particle we haven't talked about yet, and those are the neutrons. Neutrons, also in the nucleus, have no charge. How do we know the number of neutrons that an element has? Well, the number of neutrons an element has is determined by looking at the atomic mass or weight for that element. And in the case of carbon, that number is 12. That number 12, the atomic mass, is equal to the number of protons in the nucleus of each atom plus the number of neutrons. Those add up to give the mass of every atom on that periodic table. So that means all the mass is located here in the nucleus. This is where all the atomic mass exists. And those neutrons have no net charge. So if the atomic mass or weight equals the number of protons plus the number of neutrons, let's figure out how many neutrons carbon has in its nucleus. Atomic mass of carbon is 12. And the number of protons we already determined is 6. So what we're saying is 12 is equal to 6 plus the number of neutrons. So how many neutrons would carbon have? It also has 6 neutrons. That is not true for every element, though. We'll look at other examples in a minute where you can see that neutrons, protons, and electrons are not equal for every element. So that means carbon in the nucleus has 6 subatomic particles with no net charge. And there they are, the 6 neutrons. So these are going to be the 6 neutrons, which I'm going to try to squeeze in here. Okay, these are the 6 protons. And then you can see all 6 electrons orbiting around that nucleus. So every element on that periodic table differs in the number of protons, neutrons, and electrons. Let's look at another element on the periodic table. Let's actually start with hydrogen. And it's really helpful to look at your periodic table as I'm going through this. I recommend that you have it on your screen or you print it out. It's hard for me to keep switching back and forth. So I'm just going to draw the key information that I'm referring to, and then you can look at your periodic table if you need to. Hydrogen on the periodic table. Hydrogen is another element that you should memorize the symbol for. It's just H. It's atomic number 1, and it has an atomic mass of 1. Remember, this is the atomic number. And that atomic number tells us 2 really important things about that element. It tells us the number of protons in the nucleus of that element, and is also equal to the number of electrons that are orbiting the nucleus. So that means that hydrogen has 1 proton. It means it also has 1 electron. In every atom on that periodic table, the number of protons is equal to the number of electrons. And I didn't really mean to write that with a highlighter. That's just forgot to re-click over here. So the number of protons is equal to the number of electrons in every element on that periodic table. Remember that protons have a positive charge and electrons have a negative charge. So what that means is the number of positive charges in an atom is equal to the number of negative charges in an atom. And then, of course, those neutrons don't have any charge, so they don't count in this story. If you have an element with 1 positive charge and 1 negative charge, that means that element has no net charge. The number of positively charged particles equals the number of negatively charged particles. Thinking back to carbon, carbon had 6 protons, which are positive, and 6 electrons, which are negative. No net charge. And that is true for every atom on that periodic table. Atoms do not have a net electrical charge. Protons and electrons are equal in an atom. We're going to talk later about something called an ion, and ions do have a net electrical charge. So this is a very important distinction. Atoms, as they appear on the periodic table, are neutral. They don't have a net electrical charge. Hydrogen has an atomic weight or mass of 1. And remember that equals the number of protons plus the number of neutrons. So hydrogen has how many protons? 1. It's atomic number 1. So if the atomic mass of 1 equals 1 plus the number of neutrons, how many neutrons does hydrogen have? It has 0. Hydrogen is the only element on the periodic table that does not have any neutrons. In order to understand why, it's important to talk about the role of neutrons and also talk about what is happening with those electrons and the protons. So the protons are all positive, neutrons have no charge, and remember that these electrons all have a negative charge. So we have these 6 negatively charged particles orbiting that positively charged nucleus. So we have a positive nucleus and all these negative subatomic particles orbiting outside there. There's a very important force at work here called electrical force. Opposite charges attract. In other words, positive and negative are attracted to each other. So the positive charge of that nucleus has a slight pull on those negatively charged electrons. And that is what is holding the shape of that atom together. That atom is being held together by electrical force. Electrical force holds atoms together, and since all matter in the universe is made of atoms, then that electrical force is really holding together all matter in the universe. That's a very important force. What are those neutrons doing then? Well, just as opposite charges attract, like charges repel. So in other words, positive and positive or negative and negative, repel each other. In the nucleus, we have all these positive charges. What keeps that nucleus from just falling apart and all those positive charges just repelling each other? You've experienced this before if you've ever played with magnets. You know, if you put them together with opposite sides, they stick. If you try the similarly charged sides of the magnet, they're going to repel each other and you can feel that force. Those neutrons are separating those positively charged particles in the nucleus to keep that nucleus intact. So hydrogen just has one proton in the nucleus. It doesn't need a neutron to separate another proton. So hydrogen is the only element on the periodic table that does not have a neutron. Let's look at hydrogen. I'm just going to write an H kind of in the nucleus here. Let's look at the electrons for hydrogen. So hydrogen's atomic number 1. That means it has one proton in the nucleus. It also means that it has one electron orbiting that nucleus. And remember, this first electron shell holds a maximum of 2 electrons. So there are kind of parking spots for 2 electrons, but hydrogen only has 1 electron. So in that first electron shell, hydrogen has 1 electron and it has 1 open spot. That is very significant for hydrogen to have that 1 open spot, just as it's important that it just has 1 electron in that outer shell. The next element on the periodic table is called helium. And helium is atomic number 2, which means it has 2 protons and it has 2 electrons. So I'm going to just write helium right here. And in that first electron shell, which holds a maximum of 2 electrons, helium has 2 electrons total, so 1, 2. That means that first shell for helium is full. It can't hold any more electrons. Going to the next element on the periodic table, lithium, atomic number 3. That means lithium has 3 electrons. So again, I'm just going to write lithium's chemical symbol in the middle here. First electron shell holds a maximum of 2. 1, 2. But lithium is atomic number 3. That means 3 electrons. So that third electron is going to go into the second electron shell, which remember holds a maximum of 8 electrons. So there are parking spots for 8 in that second shell. Lithium is just going to have 1 out there in that outer shell. 1, 2, 3 total. Let's look again at carbon. Atomic number 6. I drew this before, but let's do it again. First shell holds a maximum of 2 electrons. The next shell holds a maximum of 8. Carbon's atomic number 6. That means there are 6 electrons orbiting the nucleus of carbon. They're going to fill this first shell. That's 2. That means 4 more out here in the second shell. How about neon? Atomic number 10. First electron shell holds a maximum of 2. Second electron shell holds a maximum of 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means this outer shell for neon, the second electron shell, is full. It can't hold any more electrons. Once we get beyond the second shell, if there are more, so sodium is atomic number 11. It's the last one I'm going to draw today, I promise. First electron shell holds 2, second electron shell holds 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But sodium has 11. So we need to go to the third electron shell, which remember also holds 8. So that 11th electron is going to have to go in the third shell because the first 2 shells are full. That means sodium has 1 electron out here in the outer electron shell, in that third shell. There's something very important about this story that I'm now going to write, and then we'll go back and look at what that means. The number of electrons in the outer electron shell of an atom determines the chemical behavior of an atom. This is why it's really important to understand subatomic particles, because those electrons are hugely important in determining the chemical behavior of an atom. Who bonds with whom? Who doesn't need to bond with anyone because they're perfectly fine just being by themselves. When we say the outer electron shell of an atom, what do we mean by that? We mean whatever the outermost shell is that contains electrons. So for sodium, the outer electron shell is this third shell. That is the outermost shell that has electrons. And how many electrons does sodium have in that outer shell? It has 1. So it has 11 total, but it only has 1 electron in that outer electron shell. It has 7 spaces open, available, and it only has 1 in that outer electron shell. Let's look at neon. How many does neon have in the outer electron shell? So the outer electron shell for neon would be the second shell, and it has 8. So neon has a full outer shell. So second shell is full. Another way of saying that is it has a full outer electron shell. Sorry, I wrote that really sloppy. Full. It doesn't have any space left for any more electrons in that outer shell. So again, the outer shell is the outermost one, furthest from the nucleus, that actually contains electrons. So third shell is not even there for neon. The third shell doesn't contain any electrons. So that means the second shell is the outermost for neon. Let's look at carbon. What's the outermost shell for carbon? It would be this one, the second shell. And how many electrons are in that outer shell? 1, 2, 3, 4. So 4 electrons in the outer shell for carbon. How about lithium? Second shell is the outer shell for lithium, and it only has 1 electron in the outer shell. That means 7 spots are available. Okay, one more. Helium. Helium has 2 electrons in the outer shell, meaning that outer shell is full. That's all it can hold. So helium has a full outer electron shell. Let's go back to our statement. The number of electrons in the outer electron shell of an atom determines the chemical behavior. If an atom does not have a full outer electron shell, it is reactive and unstable. And it will do something to achieve a full outer electron shell. If an atom does already have a full outer electron shell, okay, like we saw for neon and helium, then that element is stable and it's non-reactive. And it doesn't need to do anything to fill that outer shell. It's already full. So if an atom has a full outer electron shell, it is stable, it's non-reactive, and in fact, it's what we call inert. Inert means non-reactive. So helium, neon. In fact, everything in that very last column that I pointed out was going to be called column 8 is stable and non-reactive. A couple of other terms here, and then I'm going to go back to the periodic table and we're going to talk about those column numbers and how important those are in this story. Couple of quick definitions here. This one right here, outer electron shell. There's another term for outer electron shell, and that is valence shell. That is the outer electron shell. Those terms are used interchangeably. The electrons in that outer shell are called the valence electrons. The valence electrons are the electrons in that outer electron shell. So going back to this story, if I asked you, how many valence electrons does sodium have? The correct answer is 1. Sodium has 1 valence electron. And the valence shell is that third shell. Okay, now let's quickly go back and look at the periodic table and see how we can determine the number of valence electrons an atom has. One way we can do that is to sketch this. We can show where all of those electrons are located, and we call this drawing an electron configuration diagram. It's a drawing that shows where all of the electrons are located for that atom. But there's actually a shortcut for this. Let me show you that. Okay. You can see here Roman numeral 1, 2, 3, 4, 5, 6, 7, 8. If you don't remember your Roman numerals, you can write actual numbers over these columns. One way you can tell how many valence electrons an atom has is by sketching that electron configuration, looking at the atomic number, the total number of electrons that that atom has, and then sketching the first shell, the second shell, then the third shell. The other way you can is a shortcut. These column numbers tell you the number of valence electrons that that atom has. For this class, we'll not go beyond the third shell. So that means we won't go past argon in this story. Everything in column 1 has 1 electron in the outer electron shell. In other words, 1 valence electron. Everything in column 2 has 2 valence electrons. Everything in column 3 has 3 valence electrons. 4, 5, 6, 7, 8. Everything in column 8, except for helium, because helium only has 2 total, right? So it's going to fill that outer electron shell, has a full valence shell, but that first shell only holds 2. Everything else would have 8 in the valence shell. This last column, column 8, everything in this column is inert. In other words, stable and non-reactive. Those elements don't have to do anything to fill that outer shell. It's already full. Everything in columns 1 through 7, which is what we're going to concern ourselves with in this class, those elements have to do something to fill that outer electron shell to become stable. And that's going to be the next lecture on chemical bonding. The important things from this lecture to remember are the basic structure of the atom, how to read that periodic table. So looking at the atomic number and the atomic mass and being able to determine the number of protons, neutrons, and electrons that an atom has. And then how to determine how many valence electrons an atom has. So understanding that the first electron shell holds a maximum of 2 electrons, and then the second and third each hold a maximum of 8. How to draw that electron configuration diagram, and then ultimately how to write those column numbers as your shortcut for determining how many valence electrons an atom has. Okay, that's all for this lecture. The next one is on chemical bonds. Well, we'll start to see what these atoms can do to fill that outer electron shell and become stable.